All right, this is going over the next section of the chapter. I did have a brief conversation with class before we got on recording here about what's expected on the lab. I just don't have that on this recording so that we can keep it focused on entirely the next part of this. All right. So I told you at the beginning of the chapter that there are two ways. There are two things that we're going to discuss in this particular chapter. I walked around a corner and I said, hey, technically both of them are happening when I come around the corner. What are those two things? What are those two things that we were discussing? Change in direction of what? Technically both are change in direction in a way. Let me do one of them. I'll separate them like I did before, so that hopefully it makes it a little bit obvious. So here is the first one that we spent the first half of the chapter doing. What just changed direction there? Velocity. Correct. Yeah. The first part of the chapter is changing direction of velocity. What did not change? Orientation, aka the way that you're facing. Okay? Meaning that technically, even though we're talking about, say, the moon going around the Earth, do we technically care which way the moon is facing? To talk about this particular issue, there's an interesting thing that arises in the moon that some people don't hear, and that is, you guys know that we're always looking at the same side of the moon. Have you heard this? Like when, in the night sky, you are always, this is why you've probably heard this phrase, the other side of the moon is referred to as the dark side of the moon. The reason it's called the dark side of the moon is we never see it. Now, why is that a little bit strange? Well, imagine I'm going around in a circle right now, okay? Here I am going around in a circle, right? Here, look at this, okay? Facing the same way. Did I just go through 2 pi radians in a circle? Yes. Would someone at the center of the circle see all sides of me? Yes. Right here, they're looking at my right side, okay? Back side, left side, okay? Front side, and right side again. What would have to be true of the planet in order that they see, of me in this example, planet, moon, so they only see the same side of me? Yeah, and what's actually even strange about this is the period that it takes the moon to go around Earth is also the period that the moon revolves around itself. Sorry, trying to draw the light side and the dark side of the moon there. Okay? Do you know how long roughly it is? Anybody know what the revolution of the moon is? No. That would be Earth around itself, not 24 hours. Give you a hint, it's kind of how the calendar was pretty close to created. 28 days. Yeah. A little bit more, I think, a little 28 days and change, but it's 28 days. Okay? So, in 7 days, it goes through a quarter around the planet. But like I said, in the previous section, we didn't worry about which way it was facing. We didn't care which way it was facing. It doesn't bother us in the slightest. Right? I don't care which way the I haven't read it. I spin this thing in a circle. Again. Here we go. I don't care which way this is oriented, only that as I spin it around in a circle at the top, it's going that way. Yes? We don't care which side we're looking at, whether it's spinning or whatever it's doing up there, that type of thing. Okay? If a person is traveling through the air in projectile motion in a previous chapter, did we care technically what was happening to them in terms of orientation? No, we treated them as what's known as a point mass. Okay? A point mass is what you call it when you take the entire object in the situation and you assume it's at one spot. Okay? Is that true? Is it actually at one spot? No, but this is what you do when you look at a car and you simply measure it. I go, hey, how far is the car going? And early in the year, some people ask this, and we kind of stopped because I kind of gave you an answer, but I said, which part of the car? Well, I said just pick the same spot, okay, and measure to the same spot, and that would tell you displacement. Now, did this part of the car over here go through the exact same displacement? Yeah, we didn't have to worry about the entire car. We just focused on the fact that it's a point mass. Okay, now we are going to start to look at the object as though it was an extended mass, which is a fancy way of saying as it actually is, right? The mass is where it actually belongs. Okay? Or another nice way to say this is now we're going to worry about orientation. Now, we've kind of already done this. We have the basics of it. And actually, the really nice thing about this particular section is this. This is very, very similar to our conversation in kinematics. So let's review kinematics real quick so we have a good understanding and we can just draw that analogy real fast. Okay? Basics of kinematics is started off with this. What is that? And when would you use that equation? Acceleration is not constant. 0. When it's not, or another probably nicer way to say that if acceleration is 0, then velocity is constant. Yeah. Velocity is staying exactly constant. This ratio of delta x to delta t stays the same. AKA, simply put, if I told you a velocity of 4 feet per second and it was constant, what would that mean? Every second, right, I just go 1, 2, 3, 4, 1, 2, 3, there it is. Okay? And I cover 4 feet every single second. When did we have to stop using this equation? Why would that affect things?
Because the velocity is constantly changing.
Yeah, it's no longer going to stay at 4 feet a second, right? If that velocity is increasing, we're covering more space. If it's decreasing, we're covering less space. And that, of course, started with the definition of acceleration. Acceleration is the change in velocity over time, or VF minus VI over T, right? And out of this guy came kinematics, which you'll see me draw it in just a second, but I'm not going to do that yet. It was actually these two equations that pretty much kind of all expanded out into the kinematic equations, if you remember. Now, we already have an equation, a little bit, that we started with earlier in the chapter because I knew we would need it a little bit for the last thing, that has to do with this up here. What equation do we have that is extraordinarily similar to what we're looking at up here? Angular velocity, right. Angular velocity is equal to angular displacement over time. Now, unlike this equation, I will add to that, just a reminder real fast, okay, that there is kind of sort of a new equation for that. Not really, okay? It's really just this equation, but it's for a very specific angle. Unlike velocity, when we move, there's all sorts of different distances we could do. We could do inches, we could do miles, we can do all sorts of things. So there would never be an assumption that you would go this amount. But with angle, there is always a nice angle that we regularly use. What is that? What's that? Not 180. 360 or 2 pi radians. As such, we named the amount of time, we gave a name to the amount of time it takes to go in one circle, and that is period. So that, okay, let's do this, trying to draw this analogy out. I used this equation when no angular acceleration or velocity was constant, and this would mean I always cover 4 feet in 1 second. So if you had to guess where this conversation is going, guess when you use this equation. Angular velocity is constant, or meaning that you would cover the exact same amount of angle in the same amount of time. Okay, to draw that, I walked across the front of the room at a constant velocity. Let me demonstrate for you constant angular velocity now. 4 is right about here, so on 1,000 to 1,000. Okay, it's kind of a quick spin. There it is. Now, while it's kind of a quick spin, am I covering the same amount of angle in the same amount of time?
Yes.
Are all parts of my body covering the same amount of angle? I'm getting dizzy, but we'll deal with it. Okay, are all parts of my body, I should have chosen a smaller velocity. Okay, are all parts of my body covering the same amount of angle in the same amount of time?
Yes.
Yes. Are all parts of my body covering the same amount of space in the same amount of time?
No.
No. Thank you. you're getting these answers right, it would have taken me a minute to get there. Do you know why the world spins, by the way, when you're done spinning like that? It's because in your ear you have a sac of fluid that's actually used to figure out like exactly where you're at. You guys are still spinning right now, by the way. So one quick thing, by the way, that you can always do if that's ever the case. If you spin like this, try this out later. If you don't want to look ridiculous, or do it in here because I'm already looking ridiculous. I'll get it spinning again. Okay, you guys are all spinning good. Just go the opposite way. The friction in your ear then slows down that liquid from you continually spinning, and you're pretty much right back to normal, much, much faster than you would be otherwise. Just spin the opposite way a few times. Okay. So this is used when you're at a constant spin. Now the great thing is about a constant spin, that's regularly going to be the case, just like constant velocity is more often the case than acceleration, right? Think about examples of a constant angular velocity. Give me a few right now. Constant angular velocity. What you got? What's that? A clock. What else? The Earth. In multiple capacities, right? The Earth around itself, the Earth around the sun. What else?
The moon around the Earth.
Sure. We're doing some. Let's do some more examples here on Earth. A fan, okay, at full speed, because not before, right? Okay. Ferris wheel, okay, usually on the merry-go-round, playground merry-go-round. I guess horsey merry-go-round would also be very similar to the case. But in all of those capacities, you'll notice that, well, maybe not the Earth and the sun, because we didn't see the beginning of that, but like the merry-go-round example, me spinning example, the fan example, how fast do they start? 0. So does that angular velocity probably change? So what am I going to need to fit into this particular conversation here in that bottom right corner? Yeah, which would probably be known as? There we go. Angular acceleration. Now, before we actually give a symbol to it, because let's just get the concept down first, okay? You said it correctly. We are going to be changing angular velocity, right? Over time. So usually that equation of definition is actually angular velocity final minus angular velocity initial all over delta t. Notice the similarities once again. And we need a symbol for it, and we've been using Greek symbols, theta for angular displacement, omega for angular velocity, and we are going to use alpha for angular acceleration. Or if you talk to anybody from last year, fish. More specific people from last year, Jesus fish, but I don't, it's angular acceleration. Again, it's a similar conversation to omega. Do I call that W or do I call it omega? Don't call it either, call it angular velocity. Okay, that is angular acceleration. When does angular acceleration occur?
When there's a change in angular velocity.
Change in angular velocity. So in this particular example, okay, let's just do this. Spainhour walks across the front of the room and then stops. Okay, was there velocity? Sorry, when was it constant?
In the midst of
Right in the middle there, and that's when acceleration was 0. When was there an actual acceleration? When I sped up at the very beginning, when I stopped at the end. The equivalent right here, just so you can get a visual of it, is this. Okay, how fast was my angular velocity at the very beginning? 0. Was there an angular velocity in the middle? Was it mostly constant or changing? Constant. When it was constant, what is angular acceleration? 0. Okay. When was there an angular acceleration? I realize it's very redundant here, but I just want to make sure, because some people will, here's my biggest issue, and it was kind of the case here, but the fact that I think most of you guys are good over here, and they won't. Here's the biggest issue. I will give you situations where you have to tell between two of them. Like, I will say something like, what is the angular velocity of the second hand on the clock? We've done this one already, right? And what would you do? Well, you just know it goes in a full circle, so you'd use 2 pi, and then the period for the second hand on the clock is 60 seconds. You plug it in, you get angular velocity, yes? Then, I promise you this will be on the test, okay? Despite me saying this will be on the test, I can't tell you how many people get this wrong, okay? I will then say, what is the angular acceleration of the second hand on the clock. And here's what people will do wrong. They will take their angular velocity from part A, okay, and then divide by time. Does that say angular velocity divided by time? No. It says the change in angular velocity over time. What is the change in angular velocity of the second hand of the clock? 0. It doesn't change. It's already at a constant angular velocity. So what should the angular acceleration be of the second hand of the clock? 0. Okay? This is why it's very important to have that visual image of what it kind of looks like. This would be very equivalent to me saying something of the effect of, hey, what's the angular velocity of the moon going around the Earth? And again, you would say 2 pi divided by 28 days. You should convert that 28 days to seconds because we do use radians per second as standard. So you would do that. And then I'd say, what's the angular acceleration? Same conversation. If it helps, always put that, not if it helps, do it. Put that delta. That delta is there to remind you that these are not the same thing. They're not the same thing. So you cannot treat them as such. All right. Now, out of those two equations I mentioned a second ago came the kinematic equations, right? I'm not going to do all that same work like I did last time. It's a lot of similar amount of work. The great news is now, well, bad news is now we have angular kinematics. Remind me this real quick. When did you use regular kinematic equations? When there was acceleration. Okay? And what if there wasn't acceleration, what would you use? Boom. So, if it is not angularly accelerating, here you go. You have your equation already. We have already been using it. Okay? If you'd like, we switched this guy over to delta x equals v delta t, because we found it to be easier. So if you want, you could certainly go to delta theta equals angular velocity times time. Totally your call and what you're comfortable with there. Okay? So bad news is we have angular kinematics. When are you going to use angular kinematics? Or I'm going to say it a little bit differently, when angular acceleration is not 0. Oh, by the way, I don't think I asked this, but I think you got it. What should the units of angular acceleration be? Radians per second squared, yeah. And similar to meters per second squared, this is absolutely how I would write it as it's most efficient, but how I would understand it is that is radian seconds changing per second. Now the great news about angular kinematics is if you remember the kinematic equations, and I'm not going to make you write them, I will write them up here for reference. I wouldn't rewrite them unless you really want to, okay? They're basically the same thing, just change out the units, right? What were the 5 variables we regularly used in kinematics? Velocity what? Velocity final. Velocity initial. Change in time. So if you had to guess then, same here, and you got it. Okay, so here were the old equations, just as a reminder. Also, these are on your AP equation sheet. I think both sets are actually on your AP equation sheet, but here it is. Okay, delta x equals, I would not write these unless you really want to. This is just a reminder. Okay, there's an old equation. Here is your first, if you had to guess then, what's the first new equation? Oops, I almost made a mistake. Terrible. There's your first one. Next one. The one we probably used the most often. Oh my. I was going to do the wrong one. Get both of them on mine. This is probably the one we used the most often in kinematics, and as is the case, probably going to use the most often in angular kinematics. So what is the new equation? Oops, I screwed up. Okay. Velocity final equals velocity initial plus acceleration times time. So angular velocity final equals angular velocity initial plus angular acceleration times time. And finally, velocity final squared equals velocity initial squared plus 2a delta x. Again, regularly at the beginning of this chapter, people always screwed up and put delta t here for some reason. I don't know why that happens, but that's probably the biggest mistake usually made, that and forgetting squares. So a lot of times people make the same mistake here, but it's going to be angular velocity final squared Now, one of the reasons I post these up here is because actually there's going to be several times in this chapter where you are going to use these again. We'll talk about that here in just a second, but let's talk first about how we already get back and forth between two sets of variables that we have discussed, and that is this. I have this wheel, okay, and if the wheel goes without slipping, this is delta x, right? What is this here? Delta s, right? Arc length. And if there's no slipping, how do we assume those are related? They're the same, okay? And out of that equation bore the conversation that gave us angle, right? And I suggested that you start by thinking about this, that angular displacement is just arc length divided by radius. Or the best way to think about it is essentially this. You got a bike tire, okay, that travels certain distance along the ground. Probably the best way to think about it is how many radii along the ground did we just travel? And how do we do that? We simply take up delta x, which is the same as delta s, right? And figure out how many radiuses that is. And how many radiuses that is also how many radians it has gone through. Make sense? So my terrible picture up there, I got 1, 2, 3, 4, 5, 6, 7, 8, 9 radiuses by, I don't know what my distances are, I'm just making these up, but you know that if I have 9 radiuses, it's gone through 9 radians, which tells you it's turned over a little bit less than 1.5 times. Does that make sense? Okay. Bore out of that, I actually usually suggest you start to think about it actually like this, which I told you is essentially the circumference equation, right? The only difference, but I would use this guy because it's much more generic than the circumference equation, because in the circumference equation, what is the angle? Close, not what I'm looking for here. In terms of radians, 2 pi, and what is delta s? That's the circumference equation, right? So this is just the circumference equation, but a little bit more if you want to change the angle. Then, all right, so watch this. If I cover this amount of space in a certain time and it's equal to, to delta s, I could take delta s and divide by time. And when I divide it by time, that would tell me how much velocity, how many space I go to, which would actually be velocity tangential, right? But I can't just divide one side by time. I have to divide both sides by time, right? So if I divide that side by time, I get my second equation. And finally, the new equation that I'm going to add here is this. All right, so what is delta S? I'm drawing the picture here. Actually, let's change colors. What is VT? VT is how fast it's going this way, how fast it's going that way. Angular velocity is how fast this angle right here is changing. Yes? So, if I change VT, what if that would be changing its speed? What is that? What does it mean to change the speed of something? It's an acceleration. And specifically, since I'm changing speed and not direction, That would be acceleration tangential. And when there's an acceleration tangential and I change the speed on the outside, that would mean in turn, because of this equation, if I'm changing the speed, I'm also changing the angular velocity, which means you have that new equation. To help you better understand that, because I know it's messy, think of a wheel on a car. I just had a car. Where the heck did it go? Let me use this. Think of a wheel on a car. Okay, let's start off basic here. What's my speed if it's just sitting there? Zero. So what's my velocity tangential on the outside part of the wheel? Zero. What's my angular velocity of the wheel? Zero. Okay, let's start with the easier situation. The car has already been moving for a while. Okay, now the car is traveling down the road at 20 miles an hour. The car's velocity is constant. Yes? Because why? Because it covers the same amount of delta x in the same amount of time. Yes? In turn, then, it would make sense that it's covering the same amount of arc length around the outside part of the wheel in the same amount of time. Yes? Which means the velocity of the car is equal to the velocity tangential on the outside part of the wheels. Okay, let me say that again because that's not super easy for everybody to spot. Here's what I just said. Okay, I said however fast the car is going, let's go 20 miles an hour, is the exact same amount of space the wheels should cover on the outside because they're not slipping, and therefore should have the exact same velocity tangential. Yes? So if the car's velocity is constant, then the wheel's outer velocity should also be constant. Yes? And in turn, if the outside part of the wheel is going at constant velocity, would you expect angular velocity to be constant? Yes. Yes, you would. Okay? And in that vein, watch here, acceleration tangential, the change in speed, would be zero. As such, the angular acceleration, the change in omega, change in angular velocity, should also be zero. So what in that path, when would there be angular acceleration? When it starts moving, aka when there is also acceleration tangential. When the car speeds up at the very beginning, you'd expect the speed of the car to speed up, you'd expect the speed of the wheels to speed up, and since the speed of the wheels is speeding up, you'd expect it to cover more and more and more angle in the same amount of time. Simply put, it's just this right here. Okay? Here's Feinauer going in a particular angular velocity. Yes, he covers a certain amount of angle. When his fingertips are going a constant velocity tangential, he is covering the same amount of angle in the same amount of time. Yes? But if he speeds up, okay, now my fingertips are going faster, and you would expect in turn for me to also cover more angle in the same amount of time. Make sense? Okay. So, what I'm hoping to get out of this is if I say the wheels on the bus go round and round, round and round, round and round, you to be able to look at that situation and quickly deduce, is that an angular kinematic situation or is it not? Okay? And what you're looking for is simply this. What's the bus doing? The bus is at a constant velocity. That means the wheels on the outside are at a constant velocity. That would also in turn mean the angular velocity is constant, in which case if we go back to the back slide, if you want me to talk about the bus Feinauer, then I'm using that guy. If you want me to talk about the wheels, I'm using that guy. Okay? But I say the wheels on the bus go round and round, round and round, round and round, and the person has to stop in order to pick somebody up. Well, you would go, hey, what's the bus's velocity doing? Slowing down, it's decreasing. If the velocity of the bus is decreasing, in turn, that would mean that the angular velocity is also decreasing, right? And since angular velocity is decreasing, that means we have angular acceleration and acceleration tangential. Excuse me. So we no longer use that first equation, we would use angular kinematics. Does that make sense? The hardest part of this lesson, by far, is not the math. I know you guys have done angular kinematic stuff. The hardest part is twofold. One, recognizing the difference between technically like 3 sets of variables here. And that's why I was drawing this picture. This picture? Yes. Recognizing the difference between delta x, delta s, okay, delta s, and delta theta, v, vt, and angular velocity, a, at, and angular acceleration. Now this guy right here is not as big of a deal for me. The only reason that these two are different, we've already had that conversation, is because A can also be centripetal acceleration as well. How are we doing? The last thing we're going to do today in the last 3-4 minutes is give you like a quick example. And then that's what we're going to practice on a lot on Monday. It's just give you a lot of examples for you guys to work through, to practice through, to try to get the difference between these and how you use them. But honestly, as I mentioned, the math of this is not the hard part. It's when do I use what and like visualizing what it is that's going on, right? So let's actually do this before we do like a straight up example. Okay, I'm going to give you a situation. And I'm going to give you about 5 different variables, and I want you to tell me for each of these variables, are they 0, constant, or changing? I said 5. Let's go, we'll start off with 5. All right. A Ferris wheel at full speed. And I want to know, where are my notes? Oh, shoot, I don't want to miss one. Let's go delta theta. Discuss in your group for all 5 of those. Are they 0, constant, or changing? A Ferris wheel at full speed.
Angular velocity is at full speed, but it's going to be constant because there's not accelerating. It's not trying to like slow down. So that one would be constant as well.
All right, let's go. Let's actually start with what I would consider the easiest one. So I'm not going to start with the first one because we'll talk about that. Okay, angular velocity. Constant. Why? Because it covers the same amount of angle in the same amount of time. Okay, your easiest way to check that is this. Someone comes up to you and says like, hey, how much time did that Ferris wheel take to go around? And you measure. What should you find about the time it takes to go around the second time? Should be exactly the same. Now, technically, that's true of any amount of angle. It should be the same amount of time to go through one quarter as the next quarter as the next quarter. Okay, angular displacement. Let's go back up to the top then. Changing, but I'll add this when you look at this equation for the next time I do this. It's actually changing at a linear rate. Okay? Don't worry about that until I get to the next conversation. VT. Constant. Why? That's not what, that would be the explanation for angular velocity. Not because it goes to the same amount of angle, but because it goes to the same amount of space. Right? It's covered the same amount of space. Now, you're right, that does kind of go hand in hand with the angle. And notice that these two are going together. And the reason those two are absolutely going together is, of course, they are. They're related right next to each other in an equation. Next, what is angular acceleration? 0. How come? Yes, or the other way you can say that is angular velocity is not changing. Yes. All right. What about acceleration tangential? Oh, I forgot one up here. Sorry. It's also 0. Why is that 0? Yeah, hand in hand, right? So both of those are going to go 0 together. Next, acceleration centripetal. Constant, yes. How do you know that's constant? Why do you know there is, sorry, go ahead. Why do you know there is an acceleration centripetal? Yeah, it's going in a circle. When you are looking at these three, this one, and this one, all of those are not looking at orientation or the whole thing. The other three are looking at kind of the entire wheel. Okay, those three are all looking at like one point on the wheel. So like imagine that you're sitting in the wheel or in the Ferris wheel right there. Now, what about when the Ferris wheel brakes? Actually, no, let's say the Ferris wheel speeds up, like you're starting from stop. Let's not even do the Ferris wheel. Let's instead think, okay, the tire on your bike. You're sitting there, and someone gets behind you, and you take off. At the very beginning, when you take off, do all of these again. Let's go quickly through this because we're running out of time. Let's start off with the easiest one. Okay, I'm going to say acceleration tangential. No. Constant, yeah. It is there, but it is constant. Why is it constant? Let's go to the VT. VT is changing. How do you know? Like if you were looking at a bike, how would you know? I'm actually speeding up now, but yes, it's getting faster. The velocity of the bike is increasing, so the velocity around the outside of the wheel has to be increasing. Okay. What about angular velocity? Why? What's that?
Your amount of angle that you're covering changes.
Right, and this goes back to what I was talking about over here a second ago. So you just said because this is changing. Now these make it kind of makes these two appear to sort of be the same thing. That is not true. The reason that this one right here is different is because technically now you're on this equation. But I just said I just said a second ago, what was the initial speed of the bike? 0. So the initial angular velocity of the wheels is also 0. So notice here, this is to the first, this is to the first, this is to the first, and this is to the second. What that means, simply put, is this, that the amount of angle that the wheel covers up here is a linear relationship, meaning if you double the time, you double the amount of distance, simplistically put, right? But here, when it's angularly accelerating, if you double the time, what do you actually do to the displacement covered? Goes up by 4 because of that square, which should make sense because here's what I just said. Here's what should happen when you are looking at a wheel at constant velocity, and here's what should happen when you're covering a wheel that is speeding up. Why does that make sense? Because it's speeding up. Because it's covering more and more angle over time, it should have that relationship. This one should also be constant, and we won't worry about this one because it's going to be weird and icky. All right, we'll practice this on Monday.